Hey, welcome back to the stream. Today we're going to continue on our task of implementing a Python 3 NES emulator. So what we've been working on recently is working through the whole NesTest kind of ROM, and we're going to continue doing that today. We're probably going to try and implement something that can validate the output of the NesTest ROM that we're getting, so to just check instead of the way that we're doing it manually at the moment, and to just keep going on down that path as well to implement more instructions. Cool. So we had some comments on this commit somewhere. I don't know how I can find the comments, but I guess we'll just look. Here we go. So Danny says, towards the end of the stream you bowed on the bit instructions because the page you read made them sound complicated. They're really quite simple. You copy bits 7 and 6 from the value you read into the status reg, in my case negative and overflow, and then you AND. So I did read a bit more about the bit instruction, and basically, yeah, it's exactly what you're saying is, so you copy the negative and overflow values into the status register because you want them to carry over, and then basically you are just setting the 0 value based on whether the AND with the accumulator turns out to be 0. So that much we can probably do. So my implementation being negative is just copying the value, overflow is copying the value, and 0 result is checking whether that's 0 with and with the accumulator. Yeah, it's pretty cool. There was also a second comment left somewhere down here. One of these things is going to come back to bite me. Yeah, I think the way you're reading numbers, they mostly can't be negative. You're reading hex numbers 0 to FF. When the high bit is set, that means negative sometimes, C2's complement. Yeah, so it doesn't really matter how I store them, I suppose. If I'm storing a number as 255, that's going to have a high bit set, and that means it's going to be negative 127. But sometimes it won't be. So I'm going to store them like that, and where I need them to be negative, I'll just have something that can check whether the high bit is set. This probably wants to be something like value and 128 equals 0. Right, yeah. Alright, well let's find that then. So the negative bit is just going to be if the value bitwise end with 0 B1, 0 B1 yeah, so we'll end it with the binary. Yeah, I kind of like writing it in binary because it makes it a bit more obvious. And it's whether this, so the negative is this, is when this does not equal 0, which I think is what Danny had. Yeah, sweet. So we're going to have to start using a bit more bit shifting stuff. Cool, so the first thing I wanted to do was to come back and write something that can do the validation of, are we getting the expected instructions, and just do a check against this, because it's going to come in real handy later when we want to just be running through and tell us where we're going wrong. So let's do that. So let's create something that can read in this NesTest log, can pump us the lines, and then can compare to whatever we're doing. Cool. Alright. Yep, okay. NesTest log. Where is this actually stored? And then I can read this in nesttest.log. Yeah, okay. So let's read in the creating the RAM, creating the PPU, creating the CPU. So I kind of want to add an argument to this thing, which is going to say whether we pass the NesTest log. So the ROM path, pass to NesROM, and then parser dot add argument. We'll say is this test ROM. The meta variable is going to be t. The type is going to be string. Nah. Kind of want it to be a bool. How do we just have a flag argument? So Python 3 argument parser. That's a creative way to spell some of those things. Should work. Alright, argparse, process some integers, int dash dash sum. Yeah, we kind of want to do this const sum. Default max section store. We kind of just want to add a flag. Yeah, so this dash dash foo. And then how do we pull them out? Name or flag. Yeah, okay, so let's just do that. So let's just add parser.argument dash dash test. So are we running the test ROM? And then we can just say check if we're running the test ROM. So if args.test. So let's just check that should come up false for now. And then if we pass in the test ROM with the dash dash test flag, it should come up not as none. Expected one argument. Huh. Okay, so the flags have got to come before the R. Right, dash dash test, true. Okay. So if args.test should return true. Yep. Okay, so we just need to put test and something after it. Whatever. It's not a great way of doing it, but it'll work for now. So let's load in the NesTest.log. So we want to open the file. So with open NesTest.log, we want to be reading it as NesTest file. And then we want to just read all the lines into an object. Read lines. Cool. And now this object we can pass into the CPU, but let's just check that it is what we expect. NesTest lines, yeah. So this looks around right. What I'm going to do is just create something that can parse these files, because that's kind of how I like to roll. So let's create a new Python file and call it NesTest. So we'll have a NesTest log class which we can pass in the lines to. And then we'll store that, self.lines equals lines. Now what these are a list of strings, and what we really want them to be is a list of lines. So NesTest line is going to take in a line which is a string, and then it's going to parse some stuff and create itself an object. So for the moment, let's just say self.line equals line. This is going to be a list of strings. Self.lines is going to be, so really what we want this to do is we want self.lines to be a list, and then we're going to say for line in lines, self.lines.append NesTest line. Cool. This is going to be of type list NesTest line. Alright. Let's pipate that and let's keep going. So let's create a NesTest log. NesTest log. And we'll pass it in the NesTest lines. And in fact, probably the easiest way to do that is just going to do this. So we can get rid of that local variable. Right, so now we have a NesTest log, which at the moment is just going to be a wrapper around lines, which is going to be a wrapper around some less test line objects, which are just strings at the moment. What we really want to do is create some custom methods here that are going to validate and pull out useful information for us. So let's break this down into attributes about what each line is. So a typical line, copy value, is going to look like this. And so what is that? What is this actually telling us? It's giving us a, that is our program counter, followed by our bytes, followed by our instruction, followed by A, followed by X, Y, P, SP, and our cycle. So let's have a line so we can see that, but we can also pull out the PC. So the data, so we want to split this according to something. And I think we want to kind of split it to according to spaces. So there's one space in here, two spaces in here, many spaces in here. So we're just going to parse this format. So split line equals self.line.split. And then we'll say self.pc reg equals, I'm going to call this expected PC reg, equals the first part of the line, of the split line, the instructions. Now actually I think if we split by double space here, it's going to make our lives a little bit easier. And then our expected, because now this is going to come in as one chunk, this instruction. So expected bytes equals split line 1. And our expected instruction equals 2. Now we're going to have to parse this bit differently, but this is of a known format, so that we can do. So let's do that. So self.expected A value is going to be, let's find, now if we look at this NesTest log, now that I think about it, is this going to be what we expect? Let's just open it. Yeah, so it's going to be a fixed format. So basically this A is always going to start at the same character, which is the 49th character by the look of it. So the reg part of it equals self.line from 49 onwards. And now we want to split by space. Oh, okay, but sometimes CYC. So I think basically now we want to get rid of any spaces. We just want to strip these values out. How are we going to do that? So we could either split by colon or by spaces. If we split by spaces, this gives A 0, X 0, Y 0. But we're also going to come across these. So it's probably not what we want to do. Let me think about that. I think probably the easiest way is just going to be like to hard code these things, because we actually know what these exact values are. So let's just do that. Equals self.line 49, 51 to 53. So let's see if any of this works like how we expect. Oh, good morning, Everex. Sorry. Wouldn't a scan like thing be better, easier? Yeah, it probably would be. I guess my problem is the first section, I'm not sure that we know the format. We do, you're right, it's all consistently spaced. Right, okay. I'm a goose. Oh well, we'll go back and do that. Let's look at self and let's see if these values are actually what we expect. No, so I'm off by 1 on this thing. So the expected A is going to be that. The expected Y is going to be, yeah, regex with group matching. Yeah, I think you're right. I think regex is going to be the cool way to do this. Let's do it. I apologize for my regex. This should be interesting. I was using a really cool site the other day though called regex101.com, I believe. No. Oh, yes. Which is really awesome. So let's copy a line out of this and then match it on this thing. So here's my test string. Let's make this a bit bigger. And what's the regular expression that we want to use? Yeah, this is definitely a better way to do it if I can get it working. So there's also regular expressions.info. Cool. Look, I'll pull that up and I'll open that as well. But I'll start using this one. So basically here what we want to do is we want to match. Alright, so we want to match. Nope, am I already wrong? Matches any does that not? Am I already Am I already wrong? So the first part, we want to capture a character. Your pattern does not match the subject string. I'm already wrong on regex. Was that? Did I accidentally put something there? What the hell did I have there? Oops, I had an X there for some reason. Alright. So the first part that we want to capture is going to be the first characters, including white space. Alright, so so the first word until we hit a space. Then we're going to hit some white space, which is before. Oh, I didn't realize you could do that. There, so dot 4. Yeah, sweet. And then, what is white space? Any digit, any word character. Blur. Any white space character /s. So we kind of want to do the correct amount of white space characters, and then we want to do something that is 8, 6, 7, 8 long. Any amount of white space. Then this is going to be not of a fixed length. I suppose it is kind of going to be of a fixed length, but it's going to be of a huge fixed length. So instead of doing that, I think I'm just going to do... yeah, you're probably right. I could just do like 20, 30, 2. Alright, and then that I can just parse the spaces out of. Let's get another group going here, which is going to be our A group. So I actually want to say that there's an A group here which I don't really care about, and then I just want to get the next 2 characters. This is going to be something that we repeat, except we sub in X. There's going to be a space here. Why not let the regex already split out the JMP? I don't know what the format of this is though. I haven't looked at this. Because some of these are a bit weird where they have extra things. But you're right, I could probably parse out the first... Yeah. God, I don't even know. I could probably parse out the first 3 characters, which will allow me to put out the name of the instruction. And then the rest of it's just data. That is true. If you're already parsing. I am, I think. Are they always 3 characters? Yeah, they're always 3 characters. Alright, so let's get that into a group. So, 3. I mean, just instruction. Yeah. Oh, that didn't work. Whoa. So space, that, 8 characters. Nope, 9 characters. Whoa. Whoa, okay. What happens if I get rid of that? That's working. Oh man. Doing something wrong there. Right. Because then this goes too far. This should be 29. Ha! That's right. I'm happy to answer whatever questions. I think the reality is I evidently need a fair amount of help with regex stuff, so even if things are too late, they're probably going to help me figure out some stuff that I actually don't know anyway. 2 characters. P is going to be 2 characters. Holy crap. SP is going to be 2 characters long. And then CYC is going to be... So CYC is going to be 3 characters long. My regex sucks as well. Yeah, regex is not a tool I turn to often, to be honest with you. Cool. Yeah, here we go. I should definitely go through this. But I think for now, this is probably going to get us what we want. Admittedly, it's not great, but this will chuck us out into the formatted thing that we want. So let's do that. How do I use regex? re.search? I can never remember if it's search or find in regex you actually want to use. If you will convert it later to int, I guess that makes regex, make regex convert those hex cars. Right, so you're saying that regex can actually read it in as a hex car, I presume is what you're saying. You can also make it pass the hex into decimal. Right, that's pretty cool. Is that something that it will let it convert that int, I guess? Make regex convert. Instead of dot, use the hex thingy. Right, okay. I see what you're saying. So regex hex. Regex parse hex. Yeah, you wouldn't use the dot with the proper thingy. Where's that site that you linked me? I'll go to that. Hopefully that'll... Oh, hang on a second. Alright, I'm back. Old friend arrived back in the country. Python's so scary. Nah. Python is beautiful. Let me check it out. /h. Alright. Hex. Yeah, so if I do a /h instead of the dot. Okay. So if I do a /h on this one, right, so it doesn't, maybe you're wrong about converting it, but at least with /h you'll know if the input is bad. Parsing, yeah, parsing is very great. /h is either a horizontal depending on the implementation, I guess not then. Parsing is sexy, I agree. Alright, well let's go back to the dot then. Let's copy this in. I'm a total newbie on it. It's definitely very easy to learn. And I think compared to other languages that I've used, alright. Let's find the Python regex. I'm back to this one. Let's use 3.5. So import regex.search. Perfect. So re.search. Let's import regex. Now I believe you do this like R thing. I don't exactly know why. Regex.search. Note the pattern is positive will not match the beginning of the string being searched. You might want to use the search instead of the match. Alright, so let's do search and match. Scan through this thing looking for the first thing. Match. Yeah, okay, so it doesn't really matter. I kind of want to use match because I know that it starts off here. And I'm going pattern and then string. So there's my pattern, and then I also want to pass in the string is self.line. And we're going to say our matches. Why is this complaining? Will Python be fast enough? Yeah, I don't know if Python will be fast enough. I'm hoping it will be, considering it's a NES emulator, so it shouldn't be particularly demanding. What is a NES emulator? Yeah, so Everex has kind of answered that a little bit. So the NES is the Nintendo Entertainment System, so it's an old console that came out, I think in around the 80s, and was kind of original, one of the original big consoles. So you can kind of play the original Super Mario Brothers on it. Was one of the games you could play on that. So I'll bring up an image of what that looks like. Yeah, so this kind of game, which I'm sure you've seen an image of. And yeah, so what we're doing is emulating the hardware behind the NES, which is emulating the CPU and the graphics card and the RAM and all this kind of stuff, with the idea of being we should be able to plug in NES ROMs, which are just like the data from the game cartridges, and be able to run them and have them play the game like you would have on the original NES. So that's what a NES emulator is. Cool. Python regex example, because who knows? I don't really want the how-to. I just want someone that's not bad. re.search. Yep. Cool. m.groups there. re.match. Okay. re.search. Ah, jeez. Importing it from typing. That's a fun one. Alright. So we've got our matches, and then let's see if that works. So matches.group 0. Matches.groups. Right, okay. So expected PC reg is matches.groups 0. I don't know how Python does it. Some regex engines will want you to do a regex compile first to get the conformance, and then you can return. You can use the return compile regex object. I'm pretty sure in Python you just search and then use the groups. Yeah, outside your loop do pattern equals regex compile stuff. Okay. And then pattern.matchline. Right, so in here. Oops. So let's cut that and then say pattern equals that. And we'll pass in the pattern. The pattern is also going to be a string. And we want to match to the pattern. And we just need to remember that actually we don't want to pass in the string. Compile. Yeah, okay. So we just compile the pattern. So there's the pattern. Compiled equals re.compile pattern. Compiled. I have no idea what type compiled pattern is, but let's pass that in. Alright. Cool. Yeah. I think that is right now. Although time will tell. Alright. Let's keep going. That's going to be 3 expected. What comes next? X. And then Y. PSP cycle. Y. P. SP. CYC. 3, 4, 5, 6, 7, 8. Boom. Let's see what we got. Then it's compiled pattern dot match. Right. Matches. Alright, let's look at self and let's see what we got. Nope. Matches dot groups 0. Wait, how do I? This is one of those fun times. Here we go. re.search and then give group dot group 0. Maybe group 1 will give it to me. Yeah, okay. So find group. How do I do a find and replace in this? Can I remember? Find and replace in path. Groups. Replace with group. Yep. Replace all in this file. And then we actually just want to increment each one of these numbers by 1, which I'm sure there is a really fancy way to do. But whatever. Alright, cool. Does this work? Self. Expected A, C5, F5. Not quite, but we're getting there. Alright, so what's our expected PC reg is C000. having trouble to understand the concept of class. Classes are difficult to wrap your head around, I'll give you that. Once you do, they're fantastic. But I think they're one of the more fundamentally challenging things to understand. Alright, C00. What's our expected bytes? 4C5, C5, yep. What's our expected instruction is jump. The expected... so I need to capture the instruction data. So I'm getting those 3 characters there. Then I capture yeah, that makes a little bit more sense. And now it should be C5F5. And I'll just need to remember to strip that. Yeah, cool. So let's use that pattern instead. Let's compile that. Class is an abstract idea, a thing like a person. Yep, an interest of a class. Like CBOps version. Yeah, I find classes are difficult. The difference between an object and a class is often a difficult distinction to make. But whatever X is saying is right. One is a blueprint for the class, so you can have many people, so you could have a people class, and they all share some common attributes but are all different. And an object, and so typically you instantiate an object, is another word that gets used often. You create a specific implementation of that object, of that class, sorry. So when someone is born, you create a new object of the person class. Alright, let's look. Classes are objects. That's two. Everything's objects in Python. That's a bit confusing though. Using the traditional term of object there is probably not right. It's better to use instance. That's a good point. Expected Y, 0. Expected X, 0. Expected SP, 24. That's not right. Expected PC reg is C00. Jump, C5F5. No, okay. So expected A is still C5X5. When really I want this one. I want 4 to be that. Yep. So the instruction data, I want to be 4. And then I'm going to go through and change those numbers again. Because that's a sustainable way to do software development. Alright. Yep, SP is FD. Thing is 0. Perfect. So instruction data we want to strip because we know that that's going to be weirdly done. If I cast int, will that just give me 10? Yeah, so that can figure that out. So the expected A, we kind of just want to cast it to an int. Now the real question is whether you can do that through regex. Alright. Python match int. Extract numbers from a string. Yeah, that's what I want. Yeah, okay, so you need to cast it int still. Alright. So let's turn all these expected things into something that we can use. Now, interestingly enough, we might want to display these as hex. What if I do hex of 16? Yeah, okay, so we'll need to cast that to an int before we could display that. Yeah, fair enough. That's alright. I'll just cast them. This is just something that needs to be done at, well, not compile time, I suppose, but at program start, only one off. So I'm not terribly concerned. Oh, right, these are literal hexes, aren't they? They're not ints. Oh, shit. I think it's hex dot from string. Alright. Let's find out about that. With the 0x prefix. No, we don't have that. So we can just do comma 16. Alright. This is int. And I believe cycle, is cycle gonna be? Cycle doesn't look like it's in hex. I don't exactly know why cycle isn't in hex, but everything else looks like it's in hex. Alright. Yeah, you can do, yeah. We're operating on similar wavelengths here. I get the feeling I'm figuring it out slow and steady. Slower than you, but quicker than the stream delay, which is good for me, I think. I'm doing well. I'm doing better than before. Alright, perfect. We've done that. Do I want to leave this page? Yes. Screw you, regex. Alright, so let's see if I come to here. None type has no attribute group. Yeah, okay. Let's just put a conditional breakpoint in here, which is matches is none. And then hit that up. So matches is none. So what's our line? CBD. Yep. 0409, sure. Then NOP. Right, so this is actually 4 characters for the NOP. Oh my beautiful formatting. Alright, so occasionally we'll have... Okay. Well, let's pull that back to regex 101. And let's see what happens when I insert... Wrong thing. Insert this line. Yep, so the first... What? Okay. It's one of those things where it's weird. The first 4 characters... Yep, that. We want to get any amount of white space. Yep, and then we actually want to, instead of matching 3, we probably want to just match 4, and then that's going to work in both of these scenarios. It'll give us a bit of white space in the other one when there's only 3 in the line, but it should still work, I believe. Oops. Yeah, okay. Regex. Ha! Done. If Python had a scanf, it would be even simpler. Sadly, it doesn't. Yeah, it is a shame. I mean, it has some string parsing stuff, but oh well. Cool. All right, so let's pass this the NesTest log if we need it. So this is what Cadex was talking. Oh, not Cadex. Sorry, Danny was talking about last time of whether or not it's reasonable to always be passing in the NesTest log, which obviously it's not. So how we pass that in. You could just remove the length specifier at the end, use all the characters for the very last one. Yeah, that's true. I mean, but it's always of a fixed 3 length, so if I'm doing it everywhere else, there's not really, because I'd have to capture the white space as well, which I do anyway. That's true. No, you're right, because that doesn't capture new lines by default. All right. So really what we want to do here is once we've created the CPU, instead of, we want to run the ROM, but we also want to do a validate in here every time. So instead of running the ROM, so this is loading the ROM, then I kind of want to have a separate run and load method. It's probably going to make our lives easier. So let's do load ROM. And then this stuff here, def run. Yeah, so this will just run now. So cpu.load ROM and then cpu.run. That way you'll know if there's any leftover stuff in the line. Yeah, okay. That's true. It'll tell me what's broken because the inconversion will fail. That is better than getting a null match. Very true. Alright, create the CPU, start up the CPU, load the ROM, and then run. So kind of what I want this run command to do, instead of being one run where we just loop through everything, I kind of want it to be run a single command instead of this loop. Well, I just really want it to be a step command. And then basically do this. So while true, we kind of want the CPU to step. Now this is going to be helpful for us because we want to be able to pass in this NesTest log and compare the results. So kind of what I want this to do is to return something. So step is actually, we want it to return the data, and then we either want to chuck it away or do something with it. And we actually don't need to. We can just look at the CPU, so it doesn't need to return anything. And then we can just say, so let's say testing equals false. If we are testing, testing equals true. Just so we don't have to keep checking the args. So if we are testing, now this is probably something that I don't want to run every step. So I might do it up here. So if we're testing, just step, and then we kind of want to do a CPU dot So we kind of want to compare it to the CPU. And it's going to be taking in a CPU, which is of type CPU. Right, so now this NesTest log might be referenced before assignment. Yeah, okay. So let's create the CPU. Then if we're testing, load in the thing, and then step. And if we're not testing, just step the CPU. Alright, what next? Right, so we got a CPU and we want to compare it to a line in the log. So self.index equals 0, so let's presume we start at 0, and every time we call compare, we're going to call self.index plus equals 1 at the end. And then we're going to do self.lines, self.index dot compare against the CPU. And then down here, we're going to do the same thing. So we're going to have a compare function, which is going to take in a CPU, and is going to check that they work. So return true. And it's going to return a boolean. So is correct. And we just want to return if it is correct. And actually we just want to raise results not expected. Cool, so we just want to raise an exception if our instruction results aren't expected. We probably don't need to do that. And at the moment it's just going to return true. Now we actually want it to do the proper checking. So let's do it. So checks the CPU against a log line. Alright, so let's just start off by saying, is the CPU dot PC reg so PC match equals self dot expected PC reg. So kind of what we want to do is say, is the expected PC reg equal to the CPU's PC reg? Now I think we actually want to convert this to bytes, and let's say, and then let's return PC match. So now we have a simple thing that just checks whether the PC match is correct, which it may or may not be. PC match false. Cool. So what's our expected PC reg? 49,152, and what's the CPU's PC reg? 50,000. Alright, so let's find out why this is. So this is on the first instruction, so if we look at the NesTest log, the first instruction should start at C000, which is 49,152, which is what we expect. And what we're seeing that the actual PC reg is 50,667, which is what? C5F5. Right, so we've jumped to C5F5, and this is going to be our next one. Okay, so what we're saying is that this first line needs to be validated before we execute that instruction, but after. It actually needs to be validated here. Yeah, okay. Hmm. Interesting. So what is happening is that we're validating this at the wrong place. We need to be validating it in here, but we don't really want to be passed in a test thing to this CPU. We kind of want to do it outside of that. So one thing that we could do is we could like yield here. And then when we get this back, then next time we call it, it'll could the step function return it? I kind of want the CPU to not know about the existence of this NesTest stuff. Yeah, I've forgotten what the generator syntax is here. If I call CPU.step here, well, let's see what happens. Let's just step through this. So we step in. Oh, no, it didn't work. Yeah, so I'd have to run this and then step all the way through it. I guess the alternative would be to chuck this stuff at the top, but only if instruction is none. Because if I yield here, I'm kind of executing, I'm kind of halfway between. Now let's split this out into two functions. So let's call this a identifier. So your typical CPU pipeline is going to have a couple of steps. It's going to have like a identify, execute, memory, a couple of others. But let's try stepping this up. So let's put this into an identify step, and let's put this into an execute step. So what we kind of want to do, this print should probably go up here. So what we really want to be doing is, yeah, exactly. There's going to be have to be some data crossover here, but since the CPU is the same, we can just use self. So self.instruction. Execute. Cool. And the other thing we need is the data bytes. Where do I get those data bytes from? There we go. Cool. So now we just say cpu.identify and then cpu.execute. Cool. So now when we do it, it should be after it's identified the instruction, but before it has executed it. And the PC match is true. Nice. That is way cleaner than doing anything that I was going to do. Data length. Data length? Seems to be unknown there. Yeah. It thinks it is, but it's not. This is kind of a byproduct of the way that I've done this with some mix-ins. The reality is that data length is actually not a property of instruction, it's a property of the addressing. But addressing, how do I say this? Addressing is an intrinsic, every instruction has an addressing mix-in, so I know it exists, but it doesn't exist here. I could probably just define it on instruction and then have it be overwritten. It's probably going to be the way to do it. Generic instructions. So let's have a alright, it should just be data length equals 0. Okay, and then that will get overwritten by whatever addressing you mix in. I've done this kind of instruction stuff in a bit of a weird way, where you basically inherit the functionality from different things. So a instructions, so load instruction is load a immediate is going to be made up of immediate addressing and a load instruction. You just define your identifier bytes. A load instruction is just made up of a simple function where you can, and then it defines about which bits it sets and so on. So it's this kind of bit crazy structure that I've come up with, but I kind of like it. So cool. All right, let's see if it matches on the second one. It does not. Oh, wait. PC match true, true, true. Cool. So they're all different. What if I did return not PC match, just to check that we do in fact error out? Instruction results not expected. Cool. So I'm going to have to add more things to that, to this error message. Can I do /ns here? Let's find out. So we're going to format and we're going to add in the instruction, CPU dot instruction. So what if I did that? Yeah, we can see it's a jump absolute instruction or whatever. Cool. Well, you already have, no, not all of them. I've got around 50 instructions, actually I think exactly 50 instructions implemented of, I don't know, many, this is a list of instructions. So I think it's around 150 are actually implemented. You can see there's 256 possible ones, but some aren't implemented. But then there's also unofficial instructions, which I think all of these have like things that aren't properly documented but exist. So potentially might have to do 256, but that's the maximum. But I've kind of got the framework very much set up for all the instructions, I hope. Or some of the instructions. We'll see. It's going to be, it's definitely, I've got a way to go on the CPU, but we're getting there. Cool, so the PC match, let's go the bytes match. So the expected bytes equals CPU dot data bytes. This might not work, but instruction match. CPU dot instruction, instruction data, this is going to be where it's going to get interesting. Let's go with that and see which of these actually match. So, PC match, true. Bytes match, false. Instruction match, false. Fair enough. So, our expected bytes versus our actual bytes, and our instruction versus our instruction. Cool. So this is going to be a string. Jump absolute. So we're going to say this in string of this. It's going to tell us. I'm going to define on the instruction class a override the string method. But I don't think you can. Maybe you can. Let's find out. No. There's a way to do it though. Python override class string. Yeah, they're definitely documented somewhere, but they're not official, which is kind of bleh. What happens if I do that? Nope. Repr. Nope. What about if I did this as self or string? Nope. Okay. String method for class. This is what I want. Ooh. Let's see. Types list objects themselves, so they're converted to strings by calling the string methods on their type, which is called the meta class. So you have to overwrite the string method on the meta class. Oh my god. Yeah, it's because, yeah. I changed sing string. Oh yeah, but you can call name in Python 3, thank god. Okay, name. Name may be static. Is it the name property? Yeah, I think it is, so. Nope. Ugh, god. One day, Python, I'll figure you out. Python 3 class name. Instance dot name. Alright, okay. There we go. I knew there was a way to do that. Alright. That was stupid. Let's keep going. cpu.instruction.name. Cool. And then the bytes matching is going to be more difficult. So CPU data bytes are actually bytes. Yeah, whereas my expected bytes are a string. So I kind of want to do int expected bytes, comma 16. So what if I did 4C? 76, yep. But if I did 4CC, oh, so I can't do it with spaces either. So let's presume that we pull out the right thing, maybe. We don't really care about this. So let's ignore this for now. Let's get rid of this bytes match. Yeah, the reason being that string doesn't work is that I'm never instantiating them as objects. I'm just using them as classes because they don't actually store any data. They have no state associated with them, so I never instantiate them. Alright, jump, I'm comparing. Let's compare the regs. That's probably what I really care about, to be honest. Yeah, so self dot expected A is going to be equal to CPU dot A reg. Now this is where it's going to get fun. So A, X, Y, P, SP, and then CYC we won't do for now. X, Y, P, SP, alright, and A match and X match and Y match and P match and SP match. Cool. Right, that all fits on one line. This is going to be interesting because we're comparing different types here, but let's see what we got. Alright, so PC match, true. Instruction match, false. Alright. A match, true. X match, true. True. So which ones are false? P match, which is fair enough. I knew that was going to be wrong. So CPU.status reg. Does our status reg have like a return and to int? Dot to int. And then what was the other one that was wrong? Instruction match. So our expected thing is that, and this is jump absolute. Alright. In NesTest log, are these all upper? Yeah. Boom. True. But somehow that's not true. J in JMP. There's a space. Expected instruction dot string. Cool. So this should return true. It should all return true. Okay, we're checking against this now. That's awesome. Oh man. That's nice. Alright, instruction not found 24. So how far do we get in? We're a fair way in. Instruction not found 24. So what's the 24 instruction? So now we're back to the point. We're validating that everything is working. We're checking against that. Now we need to start implementing more instructions, which is the bit instruction. Hell yeah, regex. We are on the road. So there's a thing here which explains the bit instruction as well. Holy crap, bit. Yep, and this also explains the bit instruction surprisingly well. If I can find it, test bits. So bits 7 and 6 of the operand are transferred to bits 7 and 6 of the status register. So N and V are set based on the N and V of the operand. The 0 flag is set to the result of the operand and with the accumulator. Cool. So let's implement that. So where are my base instructions? Right, so we're going to be adding another one here, which is going to be a bit instruction. A bit instruction. Which things is this going to set? So it's going to, so I think the way I've done this, yeah, it's going to set N and it's going to set V. And the 0 flag is the one that it's going to actually change depending on the results of it. We don't actually need this pass. Right. So what do I want it to do? So if I look at my generic instructions, what do? So we do care about a memory address, but that'll happen by our addressing. The value will happen by our addressing. So we just want to look at the write or the apply side effects function. So the apply side effects function is where we set bits statically, which we don't want to do. We want to do it all based on write, based on the value that we're pulling out of memory. So all we should need to do is overwrite the write function, and then basically we just want to do a cpu.statusreg.bits class bit. No, we want to do the n bit is going to be based on the thing in memory. Oh my god. Which is going to be status dot status types dot negative. So we want to set the negative bit to be the negative bit of our value. Negative and overflow set to number from memory, which is our value over here. Of operand transferred. Yep, with operand being the value. So I think this is what Danny was saying up here. Yeah. So right. So I'm going to do it in binary because that's what I kind of want to do. So we want the thing to be value bitwise with 1, 2, 3, 4. 1, 2, 3, 4. Alright, maybe doing 128 here is going to be a bit nicer. So this is going to be with our highest bit. And then we want to do the overflow. It's going to be set off the next highest bit, which is going to be 64, which I think is what is done here. Equals that, does not equal 0. Right, yeah. So we pull a value out of here, which is either going to be 0 or 1. And this is a bool. Can a bool take an int? I'm going to presume it can. And this, if this equals 1, then it is negative. negative, set to bit 7 of the last operation. So why would this be does not equal 0? You copy them into the status register. So the only thing I can think of is if negative, hi, AB, lots of numbers. Welcome. Set to bit 7 of the last operation. Alright, so let's presume that my way is wrong, but let's hope that our NesTest log thing can pick that up. And we also want to set the 0 flag based on value ANDed with the areg. So set the 0 flag based on the value done with the CPU.areg. And now Danny's probably done this as well. Value and accumulator equals 0. Right, so all he's doing here is casting this. So if this is 1, it does not equal 0, and therefore it's true. So I think Python can handle an implicit cast from an int to a bool. Let's find out. Well, that's not going to work because we haven't implemented it. And then this is just going to be 0 if the last operation resulted in a 0 value. So if it is 0, which is what he's done here. Perfect. Okay, so this is our bit instruction. Now let's implement all the different variations on that, so all the different addressing types on that. A bit instruction can just go down here. So we kind of want a, what kind of thing is it? Is it a jump, load, store? It's none of these really. I'm going to create another thing called bitwise instructions, because there's going to be a few of these. And then I'm going to literally have one called bit instructions. So let's have it be a bit. Oh, yeah, so bit immediate. So let's find out all the different types. Where are they? Yep, so there's only 2 types of addressing, 0 page and absolute. So this is going to inherit from a 0 page addressing and also from the bit instruction. And it's going to have an identifier byte of 0x24. Which I think is how I write, there needs to literally be bytes. And then we also want to have one which is going to be absolute. Addressing, which is going to have a thing of 2C. I believe. So we've implemented both of these things. Cool. Let's check that this goes a little bit further. Do we do a bit? Nope, instruction not found 24. Right. Because I've created a new file, I actually just need to import it in here. Alright, let's see. Boom, now we go further. Do we have a bit instruction? We do have a bit instruction. Nice. But now when we come down to here, when we're executing it, things go wrong. So let's put a breakpoint here and see what happens. So what's our value? Our value is none. Well, that's probably not good. So this is a 0-page thing, which is meant to be looking up some memory. Let's just jump up and see what's happened here. So the memory address is 1. So we've got an instruction. What are our data bytes? What's absolute addressing? So if I go up to the top here and I find this bit instruction, presume this is it. No, it's not going to be. This is it. So it's going to be 2401. Yep, so there's only going to be 1 byte. And it's going to be bit, yep, and 01, the value 01 equals FF. Anyway, so we're looking at the memory location 01. And the bytes in there are none. Class.getData. CPU.class.getData. So we're getting this memory address of 1. And then we're trying to get data. And get data is for, is it 0-page or is it absolute? It is 24. Right, so it's actually 0-page. Right, so you're accessing a value in the first 256 bytes. A quick solution for the earlier validation failure for those 3 bytes after instruction name, you could bytes map lambda x in int 16. Whoa. Yes. Yeah, okay, let's do that now. So instruction data match equals self.expected data is equals CPU.data bytes, and we're saying that this expected instruction data at the moment equals a string of C5 X5, C5 F5. Oh, was not the expected instruction. Which one were we? Was it this or was it the data bytes? It was the bytes, wasn't it? Oops. Okay. So data bytes match. That is way more expecting. So what are our expected bytes? Ian is put in the first space too. Yep. So let's take our bytes. We know that the first couple of characters are going to be, that 4C space is going to be, we don't need that. So we can just actually start at 2 and go on there, because that's going to be our identifier byte. So it's F5, C5. So we want to start at 3. We know that's always going to be 3 long. And then basically we just want to turn that into bytes of map lambda x. Yeah, so I'm going to do a list comprehension, but I'm actually going to do a generator comprehension, but same thing. Now, yep, so this is going to give us everything in that, and we actually just want to split this on space, and that should work. Yeah, that works. Cool. That's nice and beautiful, right? Alright. Oh, that works. Expected bytes equals data bytes, and that. Sure. Screw you, Pepe. Alright. Oh, no, that didn't work. Matches dot group 2. Oh my god, okay. So we want to strip it and then split it. Cool. Oh my god, nah, kill me. Alright, what do we got? Dun, dun, dun. 245, 197, 0, 0, 0, 16. Aha. So what the hell is matches.group 2, 3? Oh, when there's nothing! Oh man. What the hell does this return? If it's just an empty string. Ah, it's alright. Mapping's valid. Alright, so can we not split that? So wouldn't this just be empty? And then because it's empty, bytes can't cast into it. Alright. Else it's just blank bytes equals none. So now when I come down here to data bytes match, holy shit. Split it up. Yeah. Expected ints is fine, fine, fine. I'm gonna make this a list for now, just so I can see what the hell is going on. Fine, 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 fine. Fine. Fails. Invalid little int. Really would have thought that this would be fine by now. Alright. So here we go. So this is now going to bug out. What does this return? Let's just get rid of everything else. So it actually returns a single empty line. Right, okay. So I actually just need to split this up. So oh my god. If expected data But this, if this is going to return true. Man, splitting on a 0 thing. Okay. So if we have expected data, then expected data dot split and equals that, equals bytes of that. Otherwise it equals none. Alright, surely now. Data bytes match. False, okay. Whereas this equals an empty bytes. Yep, and if I did bytes empty, what if I did bytes that? Just equals bytes. Done. Alright. That should work. Cool. Alright, fix that up. Value and a width. Ah, right. Okay, to switch back to this problem. Alright, so the value that we're getting out of the memory is 0. So why is that? So if I look at my CPU, what are my memory owners? RAM, CPU. Anyway, okay, I suspect that the thing to do here is going to be go up to instruction and get data. We're going to want to go down to here, and we want to break when we're at the correct instruction. So, class dot name if bit in class dot name. I don't know why I put it there. So bit cool. So we've got a bit instruction. Let's step through and let's see what happens. So the memory address, since it's 0 package, we want to get the int out of it, which should just return 1. If it's greater than 256, which it's not. Well, indeed, we're getting there slowly. A lot of this is just a long slog, basically. There's no real, yeah, there's no real end in sight with it, which is good, but it's going. So we've got a memory address. All right, what happens here? So class.getData. Right. Let's find usages of this. So how did this work? So immediate read addressing. Sure. Sure. So how does... Ah, right, the rights to mem thing. So most things don't touch memory. So how does a load instruction work? Indexed, indirect, whatever. How does the 0 page LDA work? So the areg equals the value, and it goes from LD, which goes from instruction. Huh. So where does this come from? Or LDA in class.name. This is kind of one of those things where I've forgotten what I've done. It's a load A immediate. Okay, sure. Load A immediate, load A immediate. Alright, alright. Right, so we haven't done anything that actually reads from memory. So we kind of want it to read from memory. In some very specific circumstances. Which is going to be rough. Okay. So let's do it. So reads from memory. We don't need this to be an object anymore in Python 3. And it's going to override the get data function. Which is always nice. And it's going to do cpu.get memory address return. Right. Yeah. So here, which things read from memory? So loads read from memory. Read from mem. Holy crap, am I reads from mem? Sure. What else does? So jump doesn't read from memory. Branches don't read from memory. Nops don't. Bits are going to read from memory. Loads are going to read from memory. Stores are going to write to memory. Set bits are not going to read from memory, write to memory. Cool. All right. So now if we come back to here, we should have our memory passed in. Our value passed in. Our value is 0. Okay. So what is 128 and is going to be 0? So now if I look at this value, false. I kind of want to cast this to a bool, which is what Danny was doing. So let's do that. Doesn't equal 0. So that doesn't equal 0. Yeah, that's false. And if it equaled 1, that would equal true. I suppose I could also just bool this, right? Probably makes more sense to me. I'm going to do the bool of this. And now, instead of actually setting the 0 flag based on the value and the areg, what I was doing before was I was setting the actual status registers. So saying set the 0 bit based on the value, and then set the negative bit based on this thing. Does not equal 0. So I'm going to do the same bool cast here. Yeah, So if our value and the CPU.areg, so kind of what we actually want to do. So right bit, generic instruction. So we kind of want to return value. And what this is telling us is that it actually wants to set this value. So I kind of want to get an updated value back from this. Now if I run this, if I don't have a return statement, is updated value just going to be none? Yeah. So if updated value is not none, value equals updated value. And we want to return the value. Cool. So now when I come in here, I can just return the value ANDed with the areg. And then just by setting stuff, these 0-bit and negative bit, I say I want it to set the 0-bit, so that's this plus, and since I want to set the 0-bit based on the value ANDed with the areg, and it should handle it automatically using my existing code. Yeah, and these are different because these are going to be set. I'll set a number. Actually, it's probably easier if I just don't do this. And I just say it sets the 0-bit, sets the negative bit, and sets the overflow bit. I'm going to make it set the overflow bit as well. And we're going to say, instead of doing this stuff, we're just going to do 1. These happen automatically, and then set the 0 flag. We're going to set the 0 flag based on the value and the areg, which I believe value and accumulator equals 0. Yeah, so I want to set that flag to true if it equals 0. Cool. So now we need to implement the sets overflow bit. Sets overflow bit. And we actually want to do this based on the 6th bit. Cool. And then instruction equals false. Cool, so now that should work, like I would expect. So we now set the negative bit and the overflow bit based on the value that we read out of memory. And then we're going to actually update the Z value based on the value and the CPU and the areg and whether that equals 0. Cool. You could do not bool if you're doing bool everywhere. Yeah, where do I do that? Not bool. So that will be 1 when it's 0, and 0 when it's 1. Yeah. No, that's a good point. And I should do it here as well. If I'm going to be staying away from doing those kind of int comparisons, may as well stick to it. Alright, cool, that's bits done. Again, it's all about just getting some infrastructure in, so like just read from memory and loading the overflow bit and stuff. So we should start going faster now, maybe. Instruction results not expected. Cool. So why are they not expected? Alright. Really, I kind of want to raise this exception in here. If not valid, I kind of want to do that. So now when I hit this exception, I've got all these values available to me. Cool. Let's take a look at what's wrong. So PC match true, 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 true. P match is false. P match, okay. So what's our expected P? 228. And what's our thing? 38. Okay. So what's our status reg look like? And what's our actual expected P? So if I put this into binary, I put this into binary, let's see how they differ. Quite substantially. Okay, so what did I just execute? A bit and a BVS. So let's find the bit and then a BVS. Yep, so this is it. So we're saying that the stack pointer should be A4, and then now it should be E4. So what should it have? So let's look at what it should have been the previous one. 0x E4. And then now. So we expect it to be this bottom one, but it was previously A4. And then basically what's happened is that 6th bit, which is the overflow bit, has been set. Alright. And our actual status reg just looks like pretty different, doesn't it? Well, that's not good. Whereas the previous one, it was. So the previous one, it was that, and then we've now executed this bit instruction and everything's gone wrong. Because we haven't executed this BBS yet. Alright, let's look at that. And it's saying 01 equals FF. Store A. Store A into 01. So what's the value of the A register? Is FF. And we want to be storing that in 01. So what's our cp.getMemory 1? 0. Right, so why is that store A not actually writing to memory? So this is what's happening here. So the store A, well, let's look at that. Let's find out what's going on. Where's that store A? So let's put a breakpoint here if store A in class.name. Yeah, I know I broke it. Yeah, that's the thing that happens. But this is exactly why we have the NesTest thing hooked up now, which is good because obviously store A is not working, which is not great. So memory address we want to get is 1. Yep. What's the value that we want to write? 255. And then we actually want to write that CPU.setMemory address value. Who is the memory owner? The RAM owns that memory. And then let's set it. So if size equals numbers.byte, which it should. Oh, that's why. Where's numbers.byte? Wait. Let's go back and do that again. Oops. Yeah, I want to get the memory, get the value, write, set memory, get the memory owner, go down, size equals numbers.byte. Does that equal false? What the hell? Ah, shit. No, I need to be careful with enum comparisons. Dot value. Yeah, okay. Let's see if I have any other enums in here. Yeah, so this is the main one. So basically when I'm comparing against an enum, as I am here, what I really want to be doing is against the value. Otherwise it's not going to hit either of those if statements, and it's not going to set any memory. Alright. So now when I do it, hey, it all works now. So memory works again. I unbroke it. I'm just going to put a thing in here and because this would have picked up the fact that we weren't doing this. So basically this, if I do that, unknown number size, yeah. Whereas if I do this, it'll now work. Alright, that's bug. Cool. Cool, so we go a bit further. There's our bit, that's where we were. We've gotten around 20 instructions further down. Instruction not found 60. Rock on. Alright, where's 60? RTS. Whoa. This is where it starts getting interesting. So RTS is going to be the opposite of our jump instruction, and it's going to return us to the value that we push to the stack pointer, which is going to test a couple of things, I suppose. Alright, so we've only got one. It's a implied thing, but let's write it up anyway. So what are our base instructions? Where's my jump instruction? JSR. So this, I'm kind of doing the opposite of this instruction here. So I'm going to presume that I'm going to start at a very similar point to this. RTS. It is going to be a jump instruction, and it's not going to affect anything, any of the status regs. And it's just going to pull PC and PC plus 1 from the stack, and then it's going to make them the PC. Cool. So let's think about this. So previously we stored the PC reg on the stack, increased the size of the stack, and then jumped to that memory location. So now we kind of want to do the opposite. We want to grab the PC reg from the stack. We want to decrease the size of the stack, and then we want to jump to the memory location. Hello, Black Stealths. Welcome back. Grab the PC from the thing. Jump to memory location. Cool. Alright. Do I have a decrease stack size function? Because I kind of wanted to do this so I could just see what I was actually doing. Decrease stack size, it's going to be plus equals. Is this an interpreter or a JIT? I mean, I have no idea how to answer that question. It's not, this CPU section of it is reading in lines and executing them one by one. So it's kind of, at the moment it's not a JNT. Yeah, I don't even know what it is. Because I'm running it on the CPU. Great question. Will it be a JIT in the future? I guess that depends on what the definition of a JIT is. Because I don't know. I mean, I know what a JIT thing does, but my understanding is that it's kind of from a compiler perspective, which this doesn't really care about, but I don't know. Is compilation done during execution of the program rather than... See, I'm not really compiling anything, I'm definitely not doing just-in-time compilation because I'm not compiling anything. Switch statement, which will be compiled down to a jump table if Python does it. I mean, the way I'm implementing the instructions is just essentially a dictionary where I just do a lookup and pull the right effects statement. You know, like have the desired effects. Let's decrease the stack size, set the memory, grab the PC reg. So we actually want to get the memory. Get memory. Sets memory. And this can also take in a number of bytes. Int equals 1. Get the memory location, and then we want to get from a location. And again, size int equals 1. Num bytes. Okay. So and now we kind of want to have this same thing here. If the size is a byte, which is going to be most of the time, then we just want to return get memory. Whereas if it's a short, which is 2 bytes long, actually I might just do this quickly. I'll start using these values over instead of these magic 2s. And then basically, if I want to return 2 bytes, then I want to be getting up to low short to bytes value. Get memory. So I kind of want to be saying upper equals that, lower equals that. And then I want to be returning get memory. Yeah, I want to return upper lower. So what does get typically return? So it's going to return an int, but in this case we actually want it to return a single int but with 2 bytes. So we're going to need short to bytes, we're going to need bytes to short. And we want to return bytes to short, lower, upper. You could always just do lower and lower, upper and lower. Yeah, so I'm pretty sure that's what so that's what this bytes to short function does. I think. So I'm unsure about whether I got the upper and the lower kind of order right. I definitely need to check that, but at the moment it'll return a single int that that'll do some stuff. Alright. So let's go to this RTS and let's see what happens. Now it's not going to work at all because I'm silly and I haven't registered it as an instruction. So JSR and RTS. So this is going to be an RTS implicit, which I'm pretty sure is what, yep. And it's going to be an RTS. And the identifier byte for it is going to be 60. Cool. Alright. So now when we do this, it should register. Right, so we're going to get the memory. We want to get a short back. Now, interestingly enough, I'm passing in too many values here. So we want to grab the PC reg from the stack. So we actually want to grab the old stored. So we want to call get the memory at the SP reg, and we want to get the old PC reg. Now I think that's just what we do, right? We don't need to pulls the top 2 bytes off the stack and transfers program control to that -1. Okay, so let's see what happens, which 2 bytes we pull off if we do this. Old PC reg equals 0. So my thought is we probably want to decrease the size of the stack first, and then we want to grab the old PC reg. And now it equals 198. Now, whether or not this value is correct, who knows? But at least we're getting values now. So that's pretty cool, I think. Jump to the memory location. Cool. So what do we actually need to do? Here we were jumping CPU set memory, increase. So now we decrease the size of the stack, we get the thing, and we want to jump. So it sets it to memory address. So we need the memory address to be old PC reg. Alright. Let's keep going then. Jump RTS. Equals 198. So what if I step in here? Whoa. Not the kind of step I wanted to do. That one. Yep. Get memory element we don't really care about. Get we do care about. If numbers byte, if it's short, sure. So what's our upper and our lower? So our upper is 198, and our lower is 0. So let's go back to our log, NesTest log, and let's look for our, what's it called? JSR. In fact, let's just go to this. So when we start, what's the PC reg that we're storing? So we are storing 50,688, which I believe is probably going to be 0xC72D. Close to that. C5F5. So close to that. Alright. C5FD. That's what it's going to be. Shit. Alright, with literally 3 off. I don't know. C72D. Alright, I can actually just do this, can't I? I can just hex this. C600. Right. So our upper byte is going to be C6 and our lower byte is going to be 00. So what's C6? Int well, look, if I did 0CXC6, 198 is our upper byte and 0 is our lower byte. Cool. So we store that, and now when we come down to here, the old PC reg, we're going to jump into that, memory owner, numbers, size. So our upper is 198 and our lower is 0. So bytes to short upper lower should actually return the opposite of that. Lower, upper. Oh, it's because I flipped the argument of deep. Cool. So now, that's pretty sick. I just flipped the argument order. Just so I don't get that wrong in the future, I'm going to make these named params. Can I do that? Upper equals upper. Lower equals lower. This is a cool thing in Python 3 where you can just do purely name params. So I don't get something like that wrong. Because that's kind of frustrating. All right. Now the old PC reg should equal 50,688. That is sweet. So now when I go to this RTS, it should return us to C600, which is what we see here. And we're going back to, what's the old PC reg here? Let's turn that into hex. Should be C600. Yeah, now the only thing that's going to be bad here is that once we've done this, then I believe that the execute is going to increment the PC reg, which is bad, which is why I believe in RTS to that address +1, it is expected as the text is subject to invoke file which puts the address -1. Pushes the address -1 of the next operation onto the stack. Yeah. Interesting. Alright. So when we do this, it's going to, well, let's just do it, but it's going to come up wrong because we're going to be off by 1. No? Do we have an RTS? Oh, no, it works. Okay. So we did jump to C600, and then once we'd done that, oh, because we're already down here, we've already jumped. Nice. Yeah, okay. Done. RTS, going. We have jumps going. We have the properly storing in memory now, and we can store bytes in memory. We can pull bytes out of memory, which is pretty cool. 08. What is 0, 8? Two things with that tab open, I don't know why. Let's go 0, 8, PHP. Push processor status onto stack. So this is a stack instruction. Alright. So let's just do all our stack instructions. I'm going to put these in the bit instructions file. So let's just do that for now. Stack instructions. So let's start with PHP. Push processor status. And it's going. These are all going to be immediate, implied. So it's going to be implied addressing. Apparently done wrong. Whatever. And PHP is going to inherit from. Now the way I kind of did this, well, let's see. Let's just do it. Yeah. So a PHP instruction is not going to have any side effects. Stack is always on page 1 and works top down. Okay, the instructions are of implied mode. Have linked to 1 byte and require machine size indicated. Yeah. So we've got our PHP. And what's it going to do? It's going to push the instructions onto the stack. So it doesn't need to read a memory value. It doesn't need to write a memory value. Does it need to write anything? So typically when you write, you get a memory address and a value in, which we do not have. RTS. So I think there's just going to be a side effect function that we're going to do. Cool. Alright. We're going to apply the side effects of pushing things onto the stack. Pushes status reg onto stack. Push processor status onto stack. Pull process stack. Push accumulator transfer. Okay. So let's implement it and then see what we're going to do. So we want to grab the status. So status equals CPU dot status reg dot toInt. So we kind of want to get it as an integer, I presume, and then we want to write the status to the stack, which is going to be CPU dot set memory CPU dot spreg. Value is going to be status. Number of bytes is definitely 1 because the status is a single byte wide. And we want to increase the size of the stack after we're done by a single byte. Cool. So this function here is going to be fairly generic. Transfer x to stack pointer. So we basically got two things here. We have things that can push data to the stack pointer, and we have things that can pull data to the stack pointer. You need a push stack function. That is exactly where my brain was going to go. And I think what we need to do is just something that can push data onto the stack. Now there's no real logic behind these write and apply side effects things. This is me trying to like classify what kind of thing each function does. And I guess write I consider as something that writes a memory value or a register value, whereas the side effect is something that would, for instance here, only really affects like a status reg or something. So I think this should be a write, just because semantically it seems a bit nicer. Cool. Oops, that is the wrong thing. I'm overriding. Yeah, so we want to grab the data to write. Which we're just going to do class dot data to push, data to push. We're going to push onto the CPU reg, and then we're going to byte. This is all pretty generic stuff, so there's no real need to there's no real need to do anything crazy here. The only thing we'll have to do is in these implied addressing things. So stack push. Implied. Is it not implied? Is it implicit? Is that where I'm going wrong? Implicit addressing. Implied. I don't know. I presume that's what it means. Length of 1 byte is implied implicit addressing 1 byte. Yeah. Okay. Cool. So PHP is just going to be identifier byte equals bytes 0x. So let's just copy this crap out of here. So PHP is going to be 08. And the def data to push is just going to return CPU dot status reg dot to int. Cool. Yeah, so now we'll just override this data to push function whenever we want to do a stack push thing. And then a stack pull function is going to be very similar. Pulls data from the stack. It's going to be a puller. And we're going to grab the data to write from the stack. So we want to decrease the size of the stack first. Then we want to grab the data to write. We don't need to do that anymore. We need to know where to write to. Okay, we'll come back to that. And then write the status to the stack. So instead of that, we want to get the memory, get the data from the stack up here, stack. Pulled data is going to be from that, and now we want to write the pulled data. Data to push, and this is going to be write pulled data, CPU, and the pulled data. Cool. So now we have our PHP. Now let's write our pull, which is going to be PLP, which is going to be a stack pull. It's going to be 28 is the bytes, and write pulled data CPU.statusReg. So let's look at status and let's see how we can actually write this. We might have to create a def from int function here. Where we're going to pass in a value and then we're going to, which is presumably going to be an int. We're then going to turn that in and set all the bits based on this. So for I bit, and then we want to say if we in items. Holy crap. So I don't really care about the values anymore. We actually care about the keys. Let's say it's the key. And so we say if this is meant to be true, then self.bits key equals basically value bit shifted in some way. Probably going to be something like this. Yeah, I mean this is probably going to be wrong, but let's find out. Start from int. So this is going to set it based off the pulled data. All right. Let's keep that going. Instruction not found. 6.8. So do I do it to it? Do I do a? So I do a PHP. Okay. Let's finish 6.8. Yeah. Okay. So let's do all these then. So we got stack pushes. So we've done PHP and PLP. So now let's move on to other stack pushes. So let's push the accumulator. So PHA, implicit addressing that is going to be 6.8. And instead of that, we just want to push the areg. And then lastly, we want TX. Oh wait, this is meant to be, PHA is meant to be 4.8. So yeah, it's going to be something weird. I don't know. I'll figure it out. It's actually just going to be yeah, geez. We want the 0th bit to be set if, yeah, it's going to be value anded, so we want it to be set if it's done with I shifted by I, so 1. I'm going to put down I there. I know that's wrong, and I'll come back to that, because it is not early morning here, but my brain is still not ready for that kind of stuff. Alright, so PHA is 48. And he's going to push the A reg, and then transfer X to stack pointer is a push, which is going to be 9A. And it's going to take the X reg. Alright, and then our pulls are going to be PLP, which we've done. Then we're going to have a PLA, which is going to be a stack pull, which is going to be 6/8. And we're just going to get the A reg. And actually this probably doesn't need to, just needs to write. cb.areg equals pull data. Cool, and then the last one's just going to be exactly the same, but xreg. Alright. So instead of PLA, it's going to be TSX, which is going to be BA. That's going to be the xreg. Cool. Which font are you using? I'm using the Darkula theme on JetBrains. The font itself is Menlo. I've cranked it up to make it quite big though, just because I don't stream in the highest quality, so make it a bit easier to see. So yeah, Menlo size 18. But it's about the Darkula theme on PyCharm, also in like Sublime and stuff. I think have similar things. I think they look quite awesome. Cool. Let's keep going. Boom. So we've done our PHPs, our PLAs. This is actually going to come back to bite me. Where's the status thing? So if I think about it, oh, is it a Mac font? Oh, fair enough. I didn't realize. Yeah, I think the PyCharm font is typically pretty good whichever platform you're on, even if it is a different one. I've used it on Linux before, and it still looks nice. So over here, if we're taking the 0th key and we have a value of 2, because I think we just want to bit shift it with one bit shifted that much by I. Was that what you said? Yeah, it is. Yeah. Cool. All right. Yeah, I think that's right. Hopefully. Good thing we have the NesTest. It'll find us out. All right. The construction not found, 29. So let's go back up to here. 29. And, all right. Let's look at our trusty AND operation. And bitwise AND with accumulator. Now, I'm pretty sure the way this works is it's the same as the bit, except the bit operation does that other stuff and doesn't, this doesn't, how do I say this? So the bit sets more flags and it doesn't return the result, whereas I think this AND sets something. I'm sure. Yes, I think it stores it in the accumulator. So let's look at the NesTest log and let's find out if that looks right. A and D. So does the accumulator change? Yeah, it does change, whereas the bit doesn't change to the accumulator. Yeah, I'm not brain dead. No, you're certainly not brain dead. I think you're pretty good at this. Let's think for a second here what we actually need to do. We've got an AND. We just need an AND function. So we've got stack pulls and stack pushes and whatever. Alright, so class AND. Bitwise and with accumulator and store result. So it's going to have this thing. It's going to set N and V, N and Z. So sets negative bit is true. Sets the 0 bit is true, but it doesn't set the overflow bit. And where's bit? I can just copy basically out of bit. If I can find bit, nice. Good. So the right thing is just going to be, we don't need to set these accumulators. We just need to say CPU dot areg. Bitwise AND with the accumulator and store the result. So we get a value, and we AND it with the memory, and we store that in A. And then N and Z will be set up value, so we are going to need to do value. Alright. So the areg is going to be set to value and with the areg. Now the only problem here is we want to set the 0 and the N we actually want this to return value. Yeah, I am going to do this actually, where write can return an updated value. Value equals updated value. And now, here, we can just say return CPU.areg. Assignment can be replaced with an augmented assignment. That is true. Cool. So now it'll AND the areg with the areg, the areg with the value, and store that result there. And then the 0 bit and the negative bit will be set off whatever that result is. Okay. Now we need to actually implement all those different AND instructions. So let's go back to about bit instructions. Stack push. So let's go back to here, let's get our AND, let's find all our different addressing modes. What's going on? Oh my god. It's horrible. Please no. Sublime, save me. Alright, I'm just going to put them up on my other monitor. And use that. So we've got a suppose I could just pull this up, couldn't I? So what do we have? We've got and immediate, which is going to be immediate addressing, and an and instruction. So immediate, I think I call it immediate read addressing, just because to be clear that it reads from the instruction itself. Yeah, what are the identifier bytes? 0x identifier byte for the and, it's 29. Cool, so is there anything more that needs to be done to make this work? So what is and? It should just work. Alright. So let's do that. So we've got and immediate, need and 0 page, the bytes of which are 25, and 0 page x, which is going to be 0 page addressing, 0 page x addressing, don't know what's that's called, 0 page addressing with x, Mr. 35, so on and so forth. Absolute. Absolute is going to be 2D. Absolute addressing with x, and add x, and that's going to be 3D with y, this is going to be 39. I think you can paste if you start a comment first. Ah, yeah, that would shit. Ha, okay. Yeah. Oh well. Good to know for the future. Alright, and then we've got indirect and indirect, the other one. So this is where I always get confused about which one is which, because there's two. There's indirect indexed, indirect. I'm gonna call this indirect X. So this is the X one. I'm just gonna actually rename this because this is way too hard to figure out. And it's indexed with X addressing. Yep, and I'm going to call this one refactor indirect with Y. I might want to rename that. So indexed with X addressing, and the identifier byte for that is going to be 21, and this is going to be indexed with Y addressing. These names are not consistent at all. Oops. Refactor renamed indirect. This should be called indirect as well. This should be renamed to indirect with X. Yep, sure. This should be ranged to something, yep, sure. Int x. Yeah, I should just call them that. Whatever, doesn't really matter. Int x, int y, indirect. With x, okay. One last. With y. Refactor. Sure. Okay. And this one should be 3.1. Import. Done. Okay. There's some more instructions done. Instruction results not expected. Okay. So let's go back to this. What's wrong? A match is false, P match is false, valid. A match and P match. Alright, which instruction am I looking at? And immediate? Oh, but is this after the PLA? This is before I've executed. So what's my actual instruction look like? That's an and immediate. Okay, well, what's not matching up? The P match. So my expected P is going to be something like that. And my actual one is going to be something like that. 1 1 0 1 1 0. So it's the second to last bit is wrong. Now there's a question about whether that's the second or the sixth or something. That's probably a good question. So it's a lower bit, which means it's going to be presumably the 0 bit. So this is after I've executed a PLA, or is this after I've executed the AND? Where does this actually come in? So I identify, I print out the thing, then I come out to main, and I compare, but I haven't yet executed this instruction. Yeah, so this is pre-executing the AND instruction, but after executing the PLA. Yep, okay. Whew. I'm getting tired. Alright. Yeah, I think at this point, there becomes a certain point at which I hit a wall. I think this is probably it. We made some really good progress today, I think. The kind of the main thing that we were looking to get going was this NesTest logger comparison, which is good because it's telling me that I'm getting instructions wrong. We've implemented a few more instructions. Let's see how many instructions we actually have. If I go down to here or something. $67. Cool. So, you know, we're slowly increasing that number. Although, again, probably the main piece of work today that we did was working on that NesTest and fixing up some of the things. We can now actually push things properly, read from memory. So that's all coming together. Thank you for coming and watching, Everex. It was really good. I really enjoy it when I have people who actually know what they're doing, because I don't really. So it's kind of fun when I'm not just like banging my head against a wall the whole time. So I have people to kind of like help out. So that's really awesome. So yeah, thanks for coming along, and all of this stuff goes up on my YouTube channel just through Twitch auto import and stuff. So yeah, if you want to catch up on anything you've missed or whatever and get up to date, then it's a good way to do it. Alright, I'm going to open up the correct repository here. What do we got going? Alright, well, we've done a lot of shit, so addressing, yep. So we can now do a NesTest comparison. Yeah. Thank you, Vitels? Thanks. Let's see. So normally, screw it, I'll do it. Let's go through it. Let's see what we've changed. Updated some addressing names to be a bit more consistent. We can now get multiple memory bytes, so I can get a byte or get a short. Stack size is now working. We split up our execution into identifying and executing a command, so that we can do some logging and stuff in between. Fixed up our helpers a little bit. Add an argument to run in test mode, which is cool. Memory owners, so now memory owners can correctly return single or multiple bytes. We can now read in NesTest, do some regex testing to pull that out, and it does custom validation and make sure that everything is as we expect it. Soft.bits, it was not bool. Yeah, so the status reg can now read and write. I think this is probably where the bug is going to be, is this 1 to I suspect. It's going to be off somehow. Added an RTS, some bit instructions and instructions, stack pushes and pulls, and all those variants based on the different addressing modes. Yeah, just some other stuff. I should probably... reset these lines, discard selected lines. So they weren't really doing anything. We have a reads from memory class, which is good because previously we weren't actually reading from memory. We were just pretending. RTS, loads, stores, whatever. Cool. I'm going to add a tag as well, so let's commit that. Repository tag as episode 7. Let's push including tags. Sweet. Alright, I'm going to wrap it up. If you have any questions or whatever, feel free to shoot them at me and I'll answer, and then I'll probably head off pretty soon. Get out of here, source tree. Yeah, thanks everyone for coming. Thanks Everex for some really good advice. It's just fun to kind of stream with people. It's what I actually enjoy. It's why I do it. So yeah, thanks for coming along and having some fun. What is this, Sublime? Get out of here, Sublime. And Safari, yep. And we'll just check that that has in fact pushed, which it should have. Yeah, latest commit a minute ago. Nice. Sweet. Alright, well, I will see everybody next time. I'm kind of trying to stream twice a week at the moment, so I'll come back. This is my first time this week, so I'll come back sometime before the end of this week, probably on Saturday or Sunday or something. And yeah, thanks for coming along. Have a great day.